There you?
Thanks. So, welcome everybody. Uh, today's talk is on gradient-based optimization with applications in fuzzy. Uh, we have speaking today Dr. Barnabas Bede. He has received his PhD from Barnabas Bede University in Romania. He's held positions at the University of Oradea, Obudu University, and the University of Texas at El Paso, and the University of Texas Rio Grande Valley. Currently serves as program director for the Bachelor of Science in CS and Machine Learning at DigiPen Institute of Technology in Redmond, Washington. His research interests include explainable AI, explainable fuzzy machine learning, fuzzy sets and fuzzy systems, etc. He wrote a book on mathematics on fuzzy sets and fuzzy logic and authored or co-authored a number of research publications. And currently he is serving as president-elect of the North American Fuzzy Information Processing Society. So with that, I'll turn it over to Dr. Bede.
Yeah, thank you very much for the introduction. Yeah, I'm really glad to be able to give a talk in this competition. Last year I was a judge, and it was an awesome competition with awesome results and organization. So thanks for all the organizers. This year we have a DigiPen team, so I'm advising that team as well on the competition. They will be participating with their work. A team of two, but they are very excited. So I'm really excited with them as well. So I think I will share my presentation. Let's see where it is. One moment, I have to start this one. Yeah. So let's start. Let's talk about gradient-based optimization. The main question that I had with respect to well, before we start, can you see my slides?
Yep, they look great.
All right. Yeah, I like them here because I can make annotations quickly. So it's a little unusual format, but yeah. Anyway, so what I was in a dilemma about in this talk is where to start. How long do I need to go back on gradient and other things? So I tried to make it as much as as much as yes, with self-contained as possible, but we might need some math concepts that I'm not always able to be going back to. But stop me if if you have any questions. I'm glad to answer questions. And well, also offline, I can answer questions about the topic. Yeah, so the outline of the talk is we'll have overview of gradient-based learning in general, including deep learning and least squares methods, gradient descent algorithms. So these will be overviewed in this section. Then how they apply to fuzzy systems, and then how can we stretch this even further? How can we apply it even further into new fields in fuzzy systems? So let's start with the introduction. Yeah, so explainable AI has basically two major directions as far as I see now. The first one is to replace explainable XAI in fuzzy. Yes, so there are XAI in general has more directions, I think, but I'm not really aware of all the directions because it's a large field. But the fuzzy explainable AI has two major directions currently. One of them is replace the black box techniques with interpretable methods, such as fuzzy systems. And the other one is to directly interpret black box techniques as much as possible, extracting knowledge as a fuzzy rule basis. So both methods are valid and yeah, very interesting. And here's an example of what machine learning right now is for most of the people. Yes, it's a black box that gets an input and pushes out an output. Yeah, and we have no idea how the machine really learned the connection between inputs and outputs, and also we have no idea how the input is connected to the output. What are the rules that govern this? So to explain that is a very challenging task, and especially as the learning is based on mostly on gradient methods in this environment. So let's see what are currently in machine learning the main gradient-based methods. So here's the first view on what is gradient. So what is the gradient? The gradient of a vector field is basically the vector constructed by putting together all the partial derivatives of the vector with respect to each variable. So imagine that the x-axis is basically the x-axis is basically one of the variables, and y is another variable of a system. And in this case, you will have basically the gradient to be this blue arrow there. Yes, this blue arrow represents the vector, how fast the variable changes with respect to these variables. Now, what are these curves? Here, these are level curves. Yeah, they are constant where the function fxy that we represent is constant with different constant values. These are larger, these are going to be smaller as you go near zero. Now, gradient-based methods will rely on the gradient concept, which is a vector that is always perpendicular to the level curves. The vector gradient of f is consisting of the components of that vector are the partial derivatives of the function with respect to x and y respectively. And yeah, it's always perpendicular to the level curves. And imagine this is like a lake or a valley, and this is the minimum value. And imagine that this is the error function of a training algorithm. So our goal is to minimize the error function usually. So we want to find this this bottom of the lake basically, but in many cases we won't know where it is. So how do we find that? The first attempt, we see that the gradient, if you compute at this point, is going to be just a point. It's going to be just zero at that given point. Yes. So that's the first thing that we notice. Okay. So how do we deal with that? When we have the gradient equals zero, we can sometimes solve that problem directly. So if I'm able to say, here's the minimum, then I'm done with all the learning. I don't need to do any learning after that. Yes. So the first method is the least squares method, which exactly does that, but it needs an important thing. It needs linear dependence of the output of the parameters on the parameters of the system. So you cannot solve in general nonlinear problems, but we can solve directly and get the minimum for linear dependence. When we have a linear dependence, then how we can solve this problem? The problem can be formulated as this XW product is basically your your weights compared with the composed with the inputs x. These are the input values. These are the weights that we have, and these are the output values. When we have a linear combination, linear dependence on the input weights, then basically we can rewrite the entire input as a matrix multiplication, and this will be the output of the system. So this is what we get as the output of the machine learning algorithm. So this is the output of machine learning algorithm, and this is the output that we want, desired output. We want to match the output of the machine learning algorithm with the desired output. And to do that, there is a fantastic equation called the normal equation, this one right here, which just does that. It finds W that minimizes the error directly. Yes. Okay, now you can say, oh, well, how do we get this equation? There is an awesome formal incorrect method to derive the equation. Yeah, well, one thing you can tell, I'm more in the math field. Yeah, so you'll see more equations today than average previous talks. Sorry about that. I try to explain them carefully. So there is an elegant and incorrect formal derivation. So what do we want? This is our system's output. We want to be equal to the output of the system that we want, the desired, the training data. So this is the output on the training data, and this is the training outputs. So how do we solve this problem? First step, we multiply from the left by the transpose of x. Yeah, then we get this XTX matrix. Yeah, we multiply both sides from the left by xt. Then, to get rid of this matrix here, we multiply by its inverse here. And by that method, we actually get this normal equation that we can write, which expresses the optimal weights. This is going to be the optimal weights all the time. Yeah, so this one is a one-shot machine learning algorithm, computes the best weights possible, directly finding the minimum point of a system, but it needs linear dependence. Why do we do that? We know that fuzzy systems have nonlinear dependence usually. Nevertheless, for example, some of the fuzzy systems output has parameters that are in a linear dependence. For example, the Takagi-Sugeno-Kang systems have their consequent part linear dependence from the data, as we will see later on. Okay, so still this method can be applied in fuzzy in many situations. This is the first attempt that you would do because it's just one step. It calculates the optimal method, and that's it. Yes, so that's the normal equation. Okay, what do we do when we don't have a linear dependence? Most of the situations we won't have linear dependence on the weights, on the parameters. Yeah, kind of never. Anyway, so the case of nonlinear dependence, we can use an iterative process, which is called gradient descent learning. Yes. So imagine that we have the same situation. We have a gradient field where x0 is your initial error. Yes, on this graph. Yes. No, it's initial x0 is the initial set of parameters that you basically just randomly set up, and this is the error function of depending on x. Level sets again. Yeah, different level sets of this function. When we start training our algorithm, we will go to the next available iteration, which will be updated this way. The new updated weights for the gradient descent learning are going to be based on the old ones, minus, yeah, I forgot here something, there is a learning rate times, typically there is a learning rate that multiplies this error gradient. Del E del WK is the error gradient, and we can calculate that, and then we multiply that by learning rate eta. So basically we make small steps towards the minimum point. Yes, smaller and smaller. As we get closer to the minimum, this error gradient will be smaller and smaller as well. At this point, the minimum point, the error gradient is 0. So we get smaller and smaller steps and converging to the optimal weights. What is the danger in this? Danger is that we could get stuck in global minima, in local minima. We are looking for this minimum, the global minimum, yeah, let's say that we have a surface like this one. Then we are looking for the global minimum. But sometimes we could get stuck in local minima. And here comes in the big dilemma of exploration versus exploitation. So exploration versus exploitation. So gradient descent methods are basically on the exploitation side. Yes, so today we discussed the exploitation aspects of these algorithms. Last talk was on the exploration, more on the exploration side with genetic algorithms, particle swarm optimization. They are more on the exploration side. Nevertheless, they have some exploitation already. Yes. So let's continue. So these are the two main algorithms for deep learning. For gradient descent learning, the linear least squares method and gradient descent learning, which is iterative and works with nonlinear things as well. Deep learning, which is quite popular nowadays, is based on this on the gradient descent method. So let's overview deep learning as yeah, I think we might be able to apply similar strategy when we work with fuzzy trees that we were working with in the first presentation. So on a fuzzy tree, you would have fuzzy systems that depend on each other in a tree structure, and we could organize them by let's say layers. Yes, so layers of fuzzy inference systems basically, and that is very similar to what we have here in neural networks. So I think it's a good idea to overview how neural networks are doing learning in backpropagation, deep learning with backpropagation. So here's an example of a neural network, just one layer of it. Of course, when you have a network, you would connect multiple layers together. So this would be connected to the next layer that has multiple neurons, so on and so forth. So I just wanted to illustrate one layer, which is basically has this form W0 plus the sum of the outputs from all neurons that are coming into this neuron here with weights W1, Wn. So again, we have weights here. Then there are also other weights. These are weights between the input and the previous layer. And these could come from previous layers of the network. Yes, and we have biases, BI are biases, that basically would be added to the inputs of the previous functions. Okay, so when we want to learn in a neural network, we adopt the deep learning method, which is basically looking just at one connection between two neurons in consecutive layers. So let's assume that this neuron is in layer L here, and this is in layer L plus 1. So L being a number, I don't know, let's say this is the 10,050th layer, and this could be the 10,051st layer of the network. Well, of course, yeah. This produces an output also. I think I should draw this one here. This will be output OK. Yes, I'm using that, so I forgot to draw it probably. So output OK is basically phi of zk. Yes, phi is the activation function of the neural network. Typically, what is phi? Phi of x is a value of x. In many applications, that would be the maximum between x and 0. So it only lets through positive values. Negative values are simply erased. The graph of this activation function is this one here. This is the value function. Okay, so why is that? Basically, we want to introduce some nonlinearity. And we want to be able to give different behavior for different neurons. Okay, and the bias will change that. So the outputs are based on the inputs from the previous layer. Yes, and of course there could be here other inputs, but I'm just picking one of them. And here also there are other outputs that this output is feeding into. I'm just picking one of them. Okay, but in this connection, we have the fantastic chain rule working. So now, so gradient descent, so deep learning is basically a fancy application of the chain rule from calculus. Yes. So let's see how this really can be written. So let's assume that we are working with one data point. Yes, we have one data point. Input is X, let's say. And the output, the target output is Y hat. Yes, Y hat is what we want, the training data. Yes, let's say that X is the image of a cat and Y is classifying it as a cat. The output is our network. Our network output is that probability of cat is 0.3. Yes, and of course, we want to improve that, no? So what do? We calculate the error gradient. So we take the derivative of this expression with respect to on, the first variable. So when we do that, we get the on minus y hat will be the error, basically the loss on the output layer. So this one is possible to be calculated. What we get from the network, we initialize the network with random weights, what we want from the network, and then the difference is basically the error, the signed error, no loss. Okay, so now, so we know the error in the last layer of the network somewhere here. Then the idea is the following. I'm gonna use that to calculate the error in the previous layer, which can be then used to calculate the error in the previous layer, the contribution of the error in the previous layer, and so on. Contribution to the error from each layer can be calculated in this way. So that can be done based on the deep learning method and again, chain rule application. So we assume that now we have everything in layer L plus 1 ready. So I know all these del E del OK values. So I know all these del E del OK. But not only this one, but the ones that also connect here. Those are all known. I know all of those. Yes. If I know all of those, I can rewrite based on the chain rule the error at OJ. So here the error generated by this neuron here would be del E del OJ. If I can calculate that, then I'm done. So how do I do that? I'm going to sum up all the contributions of the errors, and the chain rule says that I'm depending on OK, how OK depends on OJ. So this is basically here the dependence on OK of OK with respect to OJ, which is basically what? OK depends on OJ through ZK, no? So I could say it's going to be del OK, del OJ, del OK. Sorry, it's backwards. I'm always making mistakes. Del OJ, del OK I'm doing, no? So then I'm gonna get here, what is gonna be that? I'm gonna have, no, I was right first. I should trust myself. Del OJ, del OK. OJ is basically depending on OK by the expression OK is phi of ZK. So depends on phi of ZK. So it's going to be basically, this should be K there. No, K in L plus 1. This is in L plus 1. Okay. Oh, no, summation is, oh, sorry. The summation is with respect to K in L plus 1. That's correct. Okay. So del OK, del OJ here. Yeah. Okay. Now I'm going to get it right, I promise. Del OK, del OJ is going to be del OK, del ZK times del ZK, del OJ. And del ZK, del OJ is going to be the coefficient of that, which is WKJ. WKJ. And that's how I'm getting this expression. And del OK del ZK is going to be just the derivative, phi derivative of ZK. Yes. So this expression is able to calculate the loss on layer L. So J is in layer L, summing up all its contributions in layer L plus 1. So this error continues to contribute to this error, to this one, and summing up all those, I can calculate this error here. This is able to basically update the weights. Then, of course, I'm going to update the weights in such a way that I, using gradient descent method, I can update the weights to optimize the network. So that's basically gradient descent for neural networks. Okay, let's look at now fuzzy systems, how they can be used with learning. So the first thing we notice is we worked a lot with Mamdani fuzzy systems, and they have the following structure: if antecedent, then consequence. And the typical rule could be formulated as follows: if X is AI and Y is BI, then Z is CI. Yes, if asteroid is near and approaching, then danger is high, for example. Yeah, that's probably something that you are considering as a rule in your systems nowadays, no? But there is a, well, how do we calculate the output of a fuzzy system? The output of a fuzzy system is calculated based on this mathematical formula here. Yeah, why I'm writing the mathematical formula? To explain why we don't use gradient descent directly on Mamdani fuzzy systems. So when we calculate the output of a Mamdani fuzzy system, first we calculate the fuzzy output. Let me go to the next picture. This, as you saw from previous talks, we calculate the firing level of each rule. Alpha 1 is firing level of rule number 1, alpha 2 is alpha 2 is firing level of rule number 2, alpha 3 firing level of rule number 3, alpha 1 is firing level of rule number 1. And based on, well, this is a system I put together for an example. We will take the this union of trapezoids kind of shape is basically the output of the system, which can be described mathematically as the maximum for I equal 1 to n. N is the number of rules. So we make the maximum about each rule of the firing level minimum with the individual output of each rule. Yes. So this is the shape b prime of y, which can be described as a function of y being your variable here. When you have this variable, then you calculate the COG, for example, the center of gravity dephasification, as basically the horizontal coordinate of the center of mass of this, looking at it as a plate. Yes. So when you have that, you would have basically an integral over b prime of y dy divided by the area of the plate. No. Now comes the question: how do I calculate the gradient of the output of the Mamdani system with respect to the inputs, or not, the parameters of the fuzzy system, fuzzy sets in the antecedents and consequences? How could I calculate that? And the answer is, it's not so easy. We cannot really get that straightforward from the applications. So that is a difficult task for Mamdani systems. Therefore, Mamdani systems are not the best, in my opinion, for gradient-based learning. They are probably better to be treated with non-parametric optimization methods. However, there is the other famous type of fuzzy system, Takagi-Sugeno-Kang fuzzy systems, that are more agreeable with us in learning methods. So how do we put together a Takagi-Sugeno fuzzy system? Takagi-Sugeno-Kang fuzzy system is listening to rules of the form: if x is ai, then z equal wi, where wi could be either a constant, could be also a linear combination of aix, of the form aix plus bi, could be also other things, but typically these are the two most popular. Let's just call it wi. That could be either just a constant or a linear term. So the output of the system is depending on the inputs via this expression. So the output of the Takagi-Sugeno system can be calculated as the weighted average of the outputs of the rule base. Yes, so these are the outputs of the rule base. So the weighted average of the outputs of the individual rules weighted by the firing level of each rule. Yes. And this is just weighted average. So there is an easy calculation here. And what we can see, for example, from this expression, when we take derivatives with respect to parameters of the system, with respect to the linear part, we have a very easy calculation. And moreover, we have a linear dependence on these. So the result would be ai of x divided by the sum of all, we could call it j, to know that this is not the same addition as in the numerator. So this is, for example, the gradient with respect to wi of this expression. So it's really easy to calculate compared to the Mamdani one. Therefore, learning especially was developed for Takagi-Sugeno systems. Takagi-Sugeno-Kang, I'm still adjusting to use Kang as well. That's the correct way to put it. Sorry about that. I should update everywhere. Anyway, so how can we see the Takagi-Sugeno system? Well, there is criticism to those saying these are less interpretable. I can fully interpret the input layer. No, this is still if asteroid is near and approaching, and as the velocity is approaching, then danger is high. But here, instead of danger is high, then I'm gonna just say danger is 2x plus 3, or danger is 4. Yes, so we just have a number in the output layer. How can we still understand that? But there is an easy way to understand it via approximation method. So Takagi-Sugeno system is a very good approximation operator, basically, which could be understood this way. When x is about, let's say this is xi here. When x is about xi, and this triangle represents the fuzzy set about xi, then the output is about wi. Output is about wi. Yes. So we can understand it, and it's explainable. Nevertheless, we still like Mamdani the best, so we will go back to that. But anyway, let's just continue with Takagi-Sugeno. And well, many authors have already observed that Takagi-Sugeno systems are good for learning algorithms, and the UNFIS adaptive network-based fuzzy inference system developed by Roger Young is the main example of such a structure. Yes, UNFIS system basically rewrites a Takagi-Sugeno rule into a network structure and learns the parameters of the system, including the output parameters here and the parameters of the antecedents as well. So how can we learn that? On the output part, we have a linear dependence, no least squares, linear dependence on the output part. Therefore, we can use least squares method, and we get the best parameter values for the output part. On the other hand, in the input part, we have nonlinear dependence. Therefore, we could use gradient descent learning. Yes. Nevertheless, once you have learned the best results for the output part, yes, your best gradient descent modified. So you have to alternate these steps, alternate kind of like a clustering algorithm where you alternate update and assign steps, updating clusters and assigning elements to clusters. You have to alternate basically learning on the output domain versus learning on the input domain, so that you converge to the global minimum of the UNFIS problem. Okay, here's the figure that Roger Young is explaining how UNFIS is working. You calculate A1 of x and A2 of x firing levels for the antecedent A1 for the different rules, firing levels for the antecedent A2. Then you compose here. Here was a product used. Product probably, well, product is used because it's the most the most smooth result that we have. Then the weights are normalized. Yes, normalization of the weights is basically taking away this fraction here. Basically, the weights are put together into one value. Like this is just going to be called in the weight alpha I. Oh, no, yeah. So you calculate normalized weights, you normalize the weights, and then update each of them. Yes. And then run these least squares and gradient descent learning methods in alternation. And this is basically the hybrid learning algorithm of the UNFIS architecture. UNFIS is also, how I see it is basically more similar to a neural network. NFIS is like a layer. So this could be the TS fuzzy system where it connects X to the Y output. And we can rewrite it using linear and value functions. So with that in mind, this is how a neural network type or Takagi-Sugeno system can be seen more as a neural network. Now we could have other layers coming into here, other Takagi-Sugeno systems connecting to here, and we could have here basically deep learning architecture with Takagi-Sugeno systems. That would be possible based on the ANFIS, but extending it in this way as an approximation operator. So let's see. Let's see an example how this still can be interpretable. Yeah, we said that the Takagi-Sugeno systems are very good for learning, but they are less interpretable. Yes, so Takagi-Sugeno system, we can see it as a neural network, no? Then we learn on this, on the network, then we it's just still a Takagi-Sugeno system, and an expert could look at the Takagi-Sugeno system and try to understand the rules. Nevertheless, these rules are less interpretable than Mamdani. But there is a possibility to approximate Takagi-Sugeno systems and Mamdani with each other. Imagine it this way. Mamdani systems are known to be approximation of anything. Takagi-Sugeno systems are approximation of anything. And in fact, we could make them approximate each other. So the Mamdani approximates the Takagi-Sugeno system, the Takagi-Sugeno approximates the Mamdani. So that's the idea here. And I should give credit to Basha Salem here, one of my master students previously. So with him, we developed this algorithm of interapproximation between Mamdani and Takagi-Sugeno systems. So here's a Mamdani system. And let's say that we have a triangular fuzzy input here. It could be any left-right shape. I just want to simplify it, but it needs to be some kind of left-right shape as here. So we have here the endpoints of that left-right shape. So we have xi minus 1 here, the left leg of the antecedents, xi is the core, and xi plus 1 the right leg of the antecedent. AI. So this is AI basically, and BI, the consequence are of a similar structure. Then we can approximate the Mamdani system by a Takagi-Sugeno system where we can calculate the parameters of the Takagi-Sugeno system based on the legs of the consequences and antecedents. And it's natural, quite natural. So what is AI? AI is basically the slope. So it's a change in y over change in x. And change in y when AI is the antecedent should be change in BI when this antecedent is considered. Yes, when this rule is firing. So we can get, and how do we get BI? That's kind of a choice we make. We should actually go through the core here. Yes. With this setup, we are able to prove a theorem. We were able to prove a theorem that, in fact, here's the main statement of the theorem. Mamdani system can be approximated with arbitrary accuracy by a Takagi-Sugeno fuzzy system of this form. Yes. And moreover, it's an interapproximation, so it works backwards too. Yes. that allows us to inter-approximate the Mamdani and the Takagi-Sugeno systems. Now, that gives birth to this situation here, where this is still work in progress. Yes, we have one example of this type, but we would want to use multiple applications. But here's the idea. We could start with a Mamdani system that we can translate via the approximation theorem into a Takagi-Sugeno. Then we can, use learning algorithms on the Takagi-Sugeno system to improve it. Yes, then I can approximate it again with the Mamdani. So I've got a new Mamdani system, and then an expert could interact with the Mamdani system that is the approximation of the newly improved PS fuzzy system. So this architecture is basically an architecture and what I think would be an awesome fuzzy interpretable neural network for many applications. We obtained one application of this with Markel Madina. He's currently at Microsoft, but he was DigiPen student, master student. In his thesis, we worked on the improving the predictions of the El Nino Southern Oscillation, and we got help from climates and climate scientists, Gad Levy and Andrew Geis as well. So what is El Nino Southern Oscillation? Is a climate phenomenon that has a huge impact on the human environment. Basically, it's an unusual warming of the ocean in certain regions around the tropics. So this oscillation basically drives the El Nino phenomenon, which causes years when the Earth is hotter than usual, or could be La Nina, which is colder than usual. So the entire global climate is driven by this El Nino phenomenon, and it's an important problem to predict it. And to predict, we used fuzzy ensemble prediction. Basically, current ensemble methods put together all these models and many others into an average, and basically we use the average as the best guess for our El Nino coefficient. There is a ENSO index that we want to predict. And we have used a system of Mamdani fuzzy rules, for example, based on historical error. If a model's historical error is low, then its weight in the aggregation should be high. So if it has been producing good output previously, then it should have a high weight in the aggregation. In the future, it's gonna most likely produce a good output. So that's our fuzzy rule base, basically. With, well, other rules we have, if it's medium, if it's this way or that way. So we have a set of fuzzy rules that we translated into a Takagi-Sugeno fuzzy system, and we learned optimal parameters using the least squares and the gradient descent combination as before. So this is our system. These are the historical errors, and we use previous months, but a couple of them, not all of them. Yes, several months we use, and we put these into one single formula, yes, which we normalize, and then we learn these coefficients, the optimal values using least squares method, and we learn update the antecedents based on these methods. These are just measurements that are from the data coming. Okay, so with that, yeah, more details on how this is put together into a least squares method. It's just technical issue. For updating the parameters in the antecedents, we use the online learning kind of approach. So what we do is basically we actually modify the weights with a little bit, and we compute numerical approximation of the gradient. Yes, we compute a numerical approximation of the gradient, and we use that in this expression. If you have too many parameters and you have really a deep dependence on the parameters, this method can be really difficult to achieve. But in the Takagi-Sugeno system, as it's not that much buried into the data, into the system, the parameters of the fuzzy system can be updated by this method. So again, the error we calculate with the modified weights, then we see whether this modification is good or bad, and basically update it that way or not. And we had some successes with this method. So for example, in 2015, we have trained our algorithm on the historical data from 8 months of how models were behaving. And this is the output. The green one is basically the result of the machine learning on the historical data. Of course, it's close because we optimize it to be the best possible, the closest possible. But then the red one is we let it run for the future 1, 2, 3, 4 months. Yes, so we let it run for 4 more months, and we compare with the traditional approach, which is the blue curve, and we see that our method was producing a better output in this case. That's not always the case. Yeah, so here our red prediction was pretty wild compared to the prediction of the blue one that we wanted to predict. Yes. So no, orange. We wanted to predict the orange one, and the blue one is the traditional approach. So it's not obvious. This is another example. Here we did better again. Yes. And after we look at the data, we were able to extract the Mamdani systems that govern the situation. And we got these examples of Mamdani systems that we obtained. Yeah, it's interesting to see how we have a lot of systems here with small weights around 0. Yes, but we can see that there were many models that produced errors like that. So that's why they have a lower weight. That's our impression. Well, so experts can then learn about the data, and we can understand better what is driving the predictions than before. So this is an example that we used. Okay, in the context of the competition, however, we have a difficult problem because there is no data. Yes, in the sense that we don't have training data available as labeled data. We don't have labeled data. So here are a couple of ideas how reinforcement learning could work with fuzzy systems and gradient-based methods here also, as the whole talk is about gradient-based stuff. So reinforcement learning is basically the learning of an agent based on information from the environment. So here's an environment, here's the maze, for example, the agent receives information from the environment, determines what state we are in, and the agent has to take an action based on the state that we are in. And if the action is right, then we get a reward. If the action is wrong, then we don't get reward, or we get a negative reward, which is basically a punishment. No, so we can see reinforcement learning is typically what is possible in game environments. So what governs reinforcement learning is Bellman's equation. So from the mathematical point of view, Bellman's equation is calculating the expected reward. So this is the expected reward. Yes. The value function is the expected reward given in a given state. And what you want is to maximize the expected reward. Yes. This could be score, for example, or survival in the asteroid smasher game, how much the ship survives and how many objects did it shoot, did it destroy. So there is a score for everything. And to maximize the score, we can use the value function, which is basically the immediate reward. I'm going to shoot an asteroid. What is the immediate reward that I get? That's R of S. And then what's going to happen next? With different probabilities, different scenarios will come next. Yes, this is the future reward. But the future reward are going to be discounted, and this is a discount factor gamma. Bellman's optimality equation says that I should maximize this with respect to my action. So I take the best action possible, then I get the most reward possible at every stage. It's kind of a greedy approach, but well, that's how Bellman's optimality equation works. There is another, okay, what is the difficulty in this method? Calculating this part looks really intimidating. So how we could do that? To do that, we can use the so-called temporal difference learning, TD learning, which is a gradient-based reinforcement method for a change. So how do we calculate that gradient? So we want to minimize, this time we want to maximize the value function. Yes, remember that we had maximum here. Maximum, yeah, we previously went in the opposite direction of the gradient. So if I go back to the first slide, let me just, sorry, I'm going to make you dizzy a little bit. Yeah, and I go back to the first slide. I don't have links, sorry. So what is here going on? The gradient is pointing outward, and I wanted to minimize the error, so I went always in the opposite direction to the gradient, kind of this way, no? But now what happens is I'm going to want to maximize my reward. Therefore, I'm going in the positive gradients direction. That way I'm going. Yes, I'm going outward to maximize the reward. Okay, so that's the difference here. I'm gonna exit to be able to go back to where I was before. Oops. I went too far, too fast. Okay, so loading is a problem here. Yeah, it doesn't like to load as fast as I want to scroll. Sorry about that. I should have used local notebook. Come on. Sorry about that. Meanwhile, I can explain that basically we want to maximize this reward. And we basically calculate a gradient and we do a a step towards the increasing gradient. Yes, so gradient ascent method will increase the value function, and we will take the action that best basically increases the value function. Yes. Okay, now it's loaded. Okay, I'm still unclear why this happened. Anyway, so how this is done? Basically, we could calculate a gradient of the value function by this method. We make a different action. Yes, we take an action. How we modify the action basically influences how we calculate the new value function. And yeah, that's it. We go with it. Now what happens is basically that we can approximate this method via a linear temporal difference, basically. And this is basically the target. This is called the target. And we are going to see why is this. This is basically the immediate reward that I'm getting from taking the next action, that I'm just going to get one action. Yes, so I'm just going to take a random action S prime. I'm going to add the immediate reward that I get from that, and the discounted future rewards that I get from the new state where I'm going to get in S prime. Yes, so I take an action A, let's say, and I get into the state S prime. I'm getting to update my reward based on this method, and then the value function changes with this. So this gradient is approximated by this method. Also, because I don't really know the S, we change the action, what is we change the state, what is the difference between states, how big is this difference, we can never measure. Nevertheless, we don't care too much because we say that this is nothing else but one constant that I can get a different constant for it, and I'm going to update with this constant being the learning rate for me. So I have a learning rate and I have a discount factor and immediate reward from an action. Yes, these are going to be alpha and gamma we set as typically numbers that are alpha is a small number, gamma is near 1 or 0.9 or something like that. And the value function is updated based on this temporal difference expression. Similarly, we could work with Q learning. Q learning calculates the quality of an action in a given state based on the same method. And here's the next idea, and here I will give credit to my other student Shivam Kumar. In his thesis, he worked on this method. So what we can do is basically update the weights based on the temporal difference method, and this is basically the gradient part. And here we have a gradient of the quality of the Q factor with respect to the weights Wi of the given parameter. And what we could do is to look at the quality and set it up as a Takagi-Sugeno-Kang fuzzy system. Yes. And based on that, our quality will be actually a good target for reinforcement learning, and we can update the weights of the Takagi-Sugeno system to get this calculated. This Takagi-Sugeno system, if we use basically this approach, can be optimized to calculate the quality function, and then to maximize that we can take the best action possible in each state, by taking the maximum of this system. So this is a way how this was used in a couple of environments. A grid world example, CartPo system, and the lunar lander environment in OpenAI Gym. So this method is also working in other area, other works. Yeah, we actually think we have a reinforcement learning based paper on Tetrix from Lin, if I'm correct. Yes, so with similar ideas. Okay, conclusions. Gradient methods are in the exploitation trade-off, in the exploitation direction. Yes, there have been successful reinforcement learning. Deep learning, not so much, but yeah, so this is not true here. There has not been that much of a successful deep learning fuzzy environments yet, in my opinion. So there is really a lot of work to be done in that direction. Yes. No, but, oh, sorry, I'm wrong. This is true. In fuzzy, deep learning was not exploited, but in gradient, deep learning in neural networks was really well studied, and reinforcement learning as well. So in fuzzy systems, gradient-based methods are also useful, and yeah, with future directions, we see to work on deep learning and deep reinforcement learning in fuzzy, but well, other methods are also valid. Took a little longer. Sorry, here are my references. Sorry about running out of time, over time. I hope.
Oh, that's absolutely okay. That's extremely interesting. Um,
Thank
I'd
you.
like to go ahead and open up for questions if anybody has any.
Thank you.
Very interesting
Okay,
that comparison of how gradient methods can be applied in Takagi Sugeno-Ken methodologies, but it's more difficult perhaps for Mandani approaches. Thank you.
Thank you. Yeah, so indeed, more difficult for Mamdani, but maybe with this workaround, we could make the learning on Takagi Sugeno while approximating it with Mamdani. We could work around the explainability barrier there.
yeah, that would be very interesting to see. So that opens the door for making things a lot easier for using the reinforcement learning methods that you mentioned, but then still being able to explain it if desired. I was curious, have you actually implemented the reinforcement learning methods that you mentioned?
Yeah, so me with Shivam Kumar. His thesis is learning of Takagi Sugeno fuzzy systems using temporal difference methods. It was 2020 master thesis. So yeah, we are still working on putting together a paper publication somewhere in a journal. And well, he worked with this update system based on temporal difference, and he completed three examples. Grid world, basically, it's a typical reinforcement learning problem where you have a grid and a mouse and a cheese, and you have to use reinforcement learning to get the mouse to the cheese. And the CartPo system is inverted pendulum, and it worked in this environment too. And lunar lander environment, where in OpenAI Gym there is an example where you have lunar lander and has to land on the surface of the moon in a reinforcement learning.
Yeah, that's
So he
great.
completed these.
Yeah, no, that's great, and especially relevant to us because we use some of those OpenAI gems examples internally as well.
Yeah, I'm trying to encourage him to get paper publication after his master thesis, and we will try to get that rolling. I hope I will be able to get a publication which is more widely available. Yeah, I
it'd be
think I can get
interesting
his
if.
thesis. Sorry.
Oh no, I was just gonna say I'm excited to see some of this stuff, especially if you guys decide to do it for the competition. But I guess we'll see.
Yeah, I don't know if the team will decide to do it for the competition. Yeah, they are very excited about both reinforcement learning and both fuzzy systems and more of the traditional, and more of the not traditional, non-parametric optimization too. But we will see what they will be using.
Yep. As a reminder to everybody watching, we have no restrictions on the learning method. You are free to use any gradient or non-gradient based optimization that you would like. So.
And mix them too. Who knows?
Yeah. Yep. That's also an option.
We could get more. Yeah. For example, in machine learning, many times you would do an ensemble prediction. You would try different methods and then do an average of them at some point. And that's kind of important. I'm not sure if that's reasonable here, but anyway,
Yep,
explainability would possibly suffer in that case, but I don't know.
Well, thanks again for a great talk, especially relevant to the competition. Really nice to see the bridging the gap basically between some of the stuff that you see commonly in the fuzzy world and then what you see in the modern neural network communities. So especially if it allows us to utilize some of the methods that they've developed too, that's all the better.
Yeah, I'm very excited, and thank you so much for inviting me. I'm really excited to participate in the competition, and we are looking forward to see you in next conference in NAFIPS.
Oh yes, absolutely.
Thank you so much, Dr. Bede.
Yeah, thanks again.
Thank you. Thank you so much.
If nobody else has any other questions, we'll call that a day.
Yeah, thank you. Sorry, I went over time quite a bit.
No,
it was
all
perfect.
Right.
Thank you.
Thank you.
Bye.
Thank you. Bye bye. Thanks.
Bye, everybody.